Hello, welcome back. We're taking a look at 2.3, the idea of differentiability today. Differentiability is pretty much the idea of a differential function being continuous, relating back to the original f of x function. So a function f of x is differentiable in the closed interval. If it's continuous on the open interval, I mean, we don't really care if there's a whole or vertical asymptote at the endpoints a and b, as long as it's continuous there. And then we're talking about the limit of the derivative term from left and right sides at a would exist then. So there are four main examples of this scenario right here, where functions will not meet this criteria. So therefore, corner and cusps are two classic examples. The idea is at the sharp turning point. So the absolute value of x, or x to the 2/3 power, creating the cusp, corner by the absolute value, are two main causes of this. You can see you have the sharp turn right here going along the curve, and then sharp turn right up. Whereas on the other side, I use a different color, so it's a little bit more obvious. So I'm kind of going down, down, and then just sharp turn to go back up. That sharp turn is talking about it not being differentiable. If we have a vertical tangent, where we have the curve ever so briefly is being perfectly vertical for it starts continuing on its way, there's other no location where it's the derivative would not exist there technically, even though it's continuous in all three of these locations. The last topic is where it's discontinuous. The function must be continuous for it to be differentiable. As we saw for examples 1 and 3, it's possible to be continuous but not differentiable, but it is impossible to be differentiable if it's not continuous. And that's what it's saying right here. If we know the derivative exists at a point A, it also has to be continuous at that same point. It's impossible for one to not be true. The converse of that is not necessarily true, as we saw for the corner, the cusp, and the vertical tangents. If it's continuous, it's also possible for it to be not differentiable. So for a question like this, there's going to be like two types of questions you're going to typically see. First of which is you're given a graph, and you're going to be asked essentially two questions. Where is it neither continuous nor differentiable? So pretty much, we don't really even care about the nor differentiable part. We're pretty much just more focused on where is it not continuous. That's essentially what we're caring about. So for part A, where is it not continuous? At x equals 2. That's where it's not continuous. For part B, where is it continuous but not differentiable? Well, that's where we're looking for sharp corners, vertical tangents, things like that. And that's occurring at x equals 5 and 7. We've got a sharp turn right there and a sharp turn right there. So that's why those would both be locations where it is clearly continuous, but it's not differentiable then. All right, so those are generally the two types of questions you'll see with this differentiability from a graph. The two parts to it. Where is it not continuous, and then where is it continuous but not differentiable? Another aspect could be dealing with a piecewise function where they ask you to find these different values of a and b, whatever letters we want to make it differentiable. So this is where that limit idea comes into play. So we know that for this to be continuous, the original function left and right sides must be the same. So we would say a times 2 squared plus 3b times 2 plus 14 equals 3a times 2 plus 5b. Then we get 4a plus 6b plus 14 equals 6a plus 5b. And we know if we subtract the 5b over, we get b. So if we subtract the 4a and the 14, we get b equal to 2a minus 14. And the reason why we're doing something like that is because this will typically create a system of two equations. Where we'll have an a and a b, or if they're using letters like, c, d, whatever else they want there. So which means the second equation comes from the derivative. So we have our derivative piecewise function. Now, where you need to be very, very careful with this idea is a and b, while unknowns, are not differentiable variables. They are representing constants. So only the x is the derivative term, so the a and the b pretty much like 2s and 5s and 7s and things like that. So when we take the derivative of ax squared, it's more the x squared is 2x, so this becomes 2ax. The derivative of 3x is 3, so this becomes plus 3b, and the 14 goes away. And on the bottom, the derivative of 3ax would just be 3a, because it's linear, and then 5b does not have an x term, so it disappears. And we're left with x greater than 2. So be very careful when you're applying your power rule derivative here, because while the power rule will work for other letters, other variables besides x, a and b don't represent differentiable variables. They represent constants, so therefore they do not affect the derivative in the same way that like the 4 or the 2 or the 3 in this case does not affect the derivative. It's all about the x. Once we have our derivative function for the piecewise function, we do the same thing. The top, 2a times 2 plus 3b equal to 3a. We substitute 2 in for x, and we set the two top and bottom equal to each other. We get 4a plus 3b is equal to 3a. So if we substitute in for b right now, we'd have 3 times 2a minus 14 equal to 3a. And now we're just solving the system. 4a plus 6a minus 42. We get 10a minus 42 equal to 3a. Negative 42 is negative 7a, so we get a to be 7, which means b, a is not 7, a is 6. Sorry about that. B, if I substitute the 6 back in, we get b to be a negative 2. So what values of a and b make this function differentiable? If a is 6 and b is negative 2, the original function would equal each other at x equals 2, meaning it's continuous. And then the derivative piecewise function also equal each other at x equals 2, meaning it's differentiable. All right, so the graph is really the main part where we'll talk about the idea of differentiability in terms of when something is differentiable, but it's also possible to see these piecewise functions. All right, so those are some basic rules. We talk about the power rule and then the basic idea of differentiability. The next set of videos is going to be talking about 3 main rules: product, quotient, and then chain rule. And those will get used fairly often, whether we're talking about polynomials or not, though obviously we're only still dealing with a polynomial derivative. All right, so I'll see you next time for that series of videos.